Bühler Motor fractional horsepower DC motors. Application engineering. Hello, my name is Gerhard Hofmann. In part 3 of the training sessions on application engineering, I will show you the use of gear motors instead of motors only. If the application requirements are low speed in combination with high torque, a gear motor would be necessary. Low speed in this case means values below 1000 RPM. Basically, these requirements could also be fulfilled with a motor only, but this motor would become very large. There are several gear designs generally available from which we have the following types in our portfolio. Spur gears, planetary gears, and worm gears. Each design has specific advantages and disadvantages depending on the application they are used in. In case the gear output shaft must be in line with the motor shaft, spur and planetary gears are used. Spur gear designs typically less noisy. Planetary gear designs can transmit more torque. In case the output shaft must be offset, the worm gear is the choice. Worm gear designs can be self-locking. It is the application, respectively the application requirements, that define the type of gearbox to be used. Space restrictions are also an indicator for the choice of the gear design. Like the motors, the behavior of the gear motors can also be described in a performance curve. We remember the performance curve of a permanent magnet DC motor. It shows the speed, current, efficiency, and power behavior depending on the torque applied to the motor shaft. The performance curve of a gear motor using a permanent magnet DC motor is typically reduced to the speed torque and the current torque curve. The curves end at the maximum torque Tmax. Higher torques could lead to an immediate failure of the gearbox. These failures are normally irreversible. Even without an irreversible damage, the curves cannot be considered as straight lines beyond the maximum torque. Therefore, load torque in the application must be lower or equal than the maximum torque Tmax of the selected gear motor. Maximum values are specified in the datasheet of the gear motors. If we look at the performance curve of the gear motor now, we see the speed versus torque and the current versus torque curve. With their no-load values, N sub 0 and I sub 0 on the y-axis intercept. The Tmax value, defining the maximum torque for the gear motor, terminates the linear range of the curves. Speed at maximum torque N sub L max and current at maximum torque I sub L max are shown here. An operating point for the gear motor T sub L must be within the linear area of the performance curve with the limit condition T sub L is less or equal Tmax. There are a few basic calculations we do coming from the motor behavior. At first, the speed of the gear motor is the speed of the motor divided by the gear ratio. N sub G is N sub M divided by I. The second one is the torque of the gear motor, which is the torque of the motor multiplied by the gear ratio and multiplied by the gear efficiency. T sub G is T sub m multiplied by I multiplied by eta sub g. The gear ratio, which is the relationship of the number of teeth in the gear train, is specified in the datasheet of the gear motor. Also, the number of stages which define the gear efficiency is stated in the gear motor specification. As an example, we look at a two-stage planetary gear motor type 161077XXX. The datasheet shows three versions of this gear motor with three different gear ratios. On the numbers, we can also see that the maximum torque, Tmax, increases with increasing gear ratios. This maximum torque is limited either mechanically by the gears in the gear train or by the torque capability of the motor. Concerning the efficiency of the gearboxes, there is a rule of thumb for our cases where we typically deal with. For spur and planetary gears, it's 90% efficiency per gear stage. For worm gears, using a two-start worm, we consider an efficiency of about 60%. Calculating the efficiency eta sub g of gearboxes with more than one stage means if each stage has an efficiency of 90%, two stages means 90% times 90%, three stages means 90% times 90% times 90%, and so on. The formula for the gearbox efficiency eta sub g therefore is eta sub g is 0.9 to the power of the number of gear stages. For example, a 5-stage gearbox calculates to 0.9 to the power of 5, which is 0.59 or 59% efficiency. As we always apply a gear motor system and not a gearbox only, it is important to know which component, motor or gearbox, is the torque limiting factor. Basically, it can be stated that for low gear ratios it's the motor, and for high ratios it's the gearbox that limits the maximum torque Tmax. To calculate the motor data, we remember the formula T sub g is T sub m multiplied by I multiplied by eta sub g. We can change this to read T sub m is T sub g divided by I divided by eta sub g. The speed of the motor is n sub m is n sub g multiplied by I. Is the calculated motor torque T sub m less than the maximum torque for the motor, the gearbox is the limiting element. Is the calculated motor torque T sub m more than the maximum torque for the motor is the limiting element. It is now again depending on the application conditions what the maximum torque is. We remember from the first training session that for continuous operation the load point should be in the efficiency maximum of the motor. For cycle operation, the load point may be up to the output power maximum of the motor. Like in the first two sessions, a practical example will show by concrete numbers how the gear motor approach typically works. The load point in a 12-volt application with continuous operation is supposed to be 50 RPM at 100 Newton centimeter load. Load speed N sub L is definitely low, which means a gear motor is needed. We need to search our portfolio first now for a gear motor with a maximum torque T sub max of equal or more than 100 Newton centimeter and a no load speed N sub 0 of roughly 50 RPM. Gear motor type 61077 contains two versions with the right maximum torque. Here it's 140 Newton centimeter. There is one version with a no-load speed of 60 rpm, which is pretty close to the required 50 rpm. We can see that 161077414 fulfills the torque requirement. T sub Lg is less or equal Tmax. This means Tmax of the 61077,414 is more than 100 Newton centimeters. Looking at the selected gear motor 161077414 in more detail, we see that this is a three-stage gearbox. From the calculation 0.9 to the power of number of stages, we calculate a gearbox efficiency to 0.9 to the power of 3, which is 0.73 or 73%. The gearbox has a gear ratio of 73.2. The calculated load point of the motor therefore is motor torque T sub m is T sub g divided by I divided by eta sub g, and this leads to a motor torque of 1.87 Newton centimeters. The motor speed N sub Lm is N sub Lg multiplied by I, which leads to a motor speed of 3660 rpm. We know that the 161077414 gear motor uses a 13021 3XX motor, where we can look at the performance curves of 1, 13021, 301 or 302 for instance. If we draw in our calculated load point of T sub Lm of 1.87 Newton centimeters, we see that we are borderline but still in the maximum efficiency range of the motor. In order to reach the required motor speed perfectly, a winding change would be necessary. This adjustment of the motor performance would follow exactly to what we have learned in session 2. In this example, for the use of a gear motor, it would be the motor that is the limiting element. The gearbox has a specified maximum torque of 140 Newton centimeters, whereas our requested load point is only 100 Newton centimeters. If we calculate the motor torque for the maximum torque at the gearbox output Tmax 140 Newton centimeters, we can see T motor max is Tmax divided by I divided by eta sub g, and this leads to a motor torque of 2.6 Newton centimeters. Our calculated motor torque T sub m is 1.87 Newton centimeters, and this is already borderline for continuous operation. Running the motor at 2.6 Newton centimeters would thermally overload the motor. The sessions so far covered the selection of basic motors and calculations to modify or adjust them to meet the performance requirements of the application. Part 4 of the training sessions will show how to do thermal calculations on the motors in order to estimate the functionality in the application under running conditions.